Okay. Last time we touched on the Merkle-Hellman knapsack a little bit. We talked about P, NNP, and EXP and all that stuff, P and P complete. Remember all that? Okay. Now it gets tougher. All right. If I can get my slide to advance. Okay. This is a picture of Ralph Merkle and Martin Hellman. Remember the beginning slide last time, I said what was the combination of those certain numbers that you could put together to equal 113? Basically what we're talking about here. What's the combination of blocks you can put to fill in this knapsack? Hence the name Merkle-Hellman knapsack. All right. Here's how it works. First of all, we need to pick a simple super increasing knapsack. Does anyone remember what super increasing meant?
I think previous numbers can't equal more than the number of the sum of the previous number can't be greater than the
There, that's the sum of the previous numbers can't be more than the number. I think you're kind of on the same track. So basically, the second number needs to be bigger than the first number. The third number needs to be bigger than the second plus the first, and so on and so forth. What happens if it's not? Does anyone know what could possibly happen?
You could have two of the same key.
I could have different keys. Yeah. Basically, there could be two answers that solve the equation, which we don't want. All right. And I must set, don't I set this every time and don't show this message again?
Yes, to be sure.
Every day it asks me that. All right, so after we pick our simple super increasing knapsack, first of all, there will be a question on that as well. You have to calculate a hard knapsack, and there's going to be a question on that as well. Okay? Then you take your hard knapsack and encrypt your message. What type of message is it? It's a specific type of message. Starts with ones and zeros. It's a binary message, right? Okay. Now, let's see how it actually works. Okay, so the receiver, so Cameron over there, he picks a simple super increasing knapsack, okay, S. He also picks a multiplier and a modulus, okay. So Cameron over there, which will be the receiver, has picked 3 items, okay. So for the simple super increasing knapsack, we have 1, 2, and 6. Could be more numbers in it. I think your assignment is 4 numbers, okay. So the 2 must be bigger than the 1. The 6 must be bigger than the 2 plus 1. So then we also pick a W and an N, a multiplier and a modulus. The N is prime, but for some of the examples and stuff, it's not always prime in my stuff. But in the real world, it would be prime. Okay? All right. Then we compute the hard knapsack. Okay? Here's how you compute it. You have to know this. It will be on 2 exams, at least. Maybe 3. The way you read this is h to the I is equal to W times S to the I mod N. In other words, the first H value will be equal to the W times the first S value mod N. So in other words, the first H is equal to W, which is 11, times 1, which is the first S value, mod 13. Everybody see that? All right. So, 11 times 1 is 11. Now, modulus. Did I cover modulus yet? Okay. Well, we're going to talk about it just to make sure. Modulus is remainder. So 11 mod 13, here's the way you do it. You take the 13, you put it in front of the 11. Then you do very basic elementary school division. So you take the second number in front of the first number, put your little divisor symbol over it. So how many times does 13 go into 11? 0. How many is left over? 11. 13 didn't fit into 11. So the remainder is 11. Okay. So H2, which would be the second value, is W again, so it's 11, times the second S value, which in this example is 2. So 11 times 2 is 22. 22 mod 13. Okay? So we take the 13 in front of the 22, Put our divisor symbol over it. 13 goes into 22 how many times? 1. What's the remainder? 9. So the answer is 9. So far, so good? I'm going to tell you where you're going to screw up. And I made sure on the test I screwed up the same way. The first example I did, 11 mod 13. Remember you put the 13 in front of the 11. You're going to want to tell me the answer is 2. You're going to do it backwards. It's just, even today, I'm like, oh, 11, 13, 2. When the numbers are close like that, and the second one's bigger, you're going to want to do it backwards. You're just going to. I know you are. So you can tell me the answer is 2 when it's not. Remember, the second number goes in front of the first number, put the division symbol on it, then get the remainder. Okay, the third one is W, which is 11 again, times the third S value, which in this case is 6. 11 times 6 is 66. Mod 13, again, 13 goes in front of the 66. And then how many times? 13 times what?
5.
Okay, so 13 times 5 is 65. The remainder is 1, so modulus is 1. Easy enough? So a hard knapsack is 11, 9, and 1. Okay? And you have a specific question on the test, calculate a hard knapsack. So the answer would be, if I give you these values, the answer would be 11, 9, and 1. So far, so good? Everyone with me? All right.
So how do you choose W and N?
You don't choose them. I give them to you.
Okay.
Yeah. That was actually be chosen by the receiver, so Roy would have picked that, or Cameron would have picked it. Whoever, the receiver is. But for this, I always give that to you. Okay.
And you also give the S.
I will give the S, I will give the W and the N, and I'll also give you the E, which we're going to see. All right. All right. So how do we send a message? So the receiver, in other words, Cameron over there, is going to send me the 11, the 9, and the 1. Now, since he's sending me 11, 9, and 1, did he send me the simple knapsack? He did not. So I don't know what he started with. Okay? So you see how that's helpful. He's sending me the hard knapsack, so I can use the simple, when I send him something, he can now use the simple super increasing knapsack to decrypt it. And the hard is based on the simple, so it's really good. Okay, so the receiver sends the hard knapsack to the sender. The receiver keeps the simple knapsack. So Cameron over there is keeping that 1, 2, and 6. He's not telling me what it is, he's just keeping it. He also keeps the W in the end. Keeps all that secret. Okay, now I want to transmit some messages. Again, it's a binary message. So my plain text in this case is 101. 010, 011. It's my plain text. Just happens to be converted into binary. So, what we do is for each digit of the plain text, we put it on top of the...
Sir, I have a question. That the plain text, which is 101, we have to convert it or it will be...
No, it's... We're encrypting it. But no, I give you the plain text, you don't mess with it. You leave it in binary, but you use the plain text to create the cipher text. That's what we're doing now. So we take the 101, which is the first 3 digits of the plain text. We take our 3 digits from our knapsack, our hard knapsack, 11, 9, and 1. And the way that you do this is 11 times 1 plus 9 times 0 plus 1 times 1 gives us 12. Everybody see that? 11 times 1 plus 9 times 0 plus 1 times 1. So we get 12. Then we take the next 3 digits, 0, 1, 0. Again, use the same hard knapsack. So 11 times 0 plus 9 times 1 plus 1 times 0 gives us 9. If you don't know it, any number times 0 is 0. Any number times 1 is itself. So the third one is 0, 1, 1. So it's 11 times 0, which is 0, plus 9 times 1, which is 9, and 1 times 1, which is 1. 9 plus 1 is 10. So our cipher text is now 12, 9, and 10. That was the second test question. Because you calculated the hard knapsacks, and now we use the hard knapsack along with the plain text, which I will give you, to create the ciphertext. So the answer to that one is 1291. Yes, sir.
So the plain text, it needs to be in binary for us to encrypt it, but are you going to just give us like the numbers?
No, I'm going to give it to you in binary.
Okay.
I'm going to give you the 101. No, I'm not going to give you a word and tell you to convert it to binary. No.
Okay.
I'm going to give you the actual 101010, just like that. And I'll make sure the correct number to match up and everything. So far, so good? Everybody got it encrypted just fine? Okay. It's a lot of steps. Okay. Now, modulus. We already talked about it a little bit, but let's look at another example. So 33 mod 8. The question is, what is the remainder? So what we need to do is, how many times does 8 go into 33? Goes in there 4 times. Okay? So 8 times 4 is 32. 33 minus 32 is 1. The answer is 1. Do not tell me the answer is 0.125. That's not the answer. So if you use a calculator, it's going to, if you do 33 divided by 8, it's going to give you 4.125. Don't tell me the remainder is 0.125. It's not. So do this, do the division to get the 4.125, then multiply 8 times 4 to get to 32, then 33 minus 32 gives you 1. Easy enough? Simple? All right. Now we get to the fun stuff. Here you have an assignment on this. Okay. And we're going to calculate the multiplicative inverse. You're going to do it exactly the way I tell you, which is 3 different ways. Okay? It says to calculate the multiplicative inverse of a number, take that number, go w to the n minus 2 mod n. So, if n is 13 and w is 11, so we're going to go w, which is 11, raised to n minus 2, okay, which is basically that, mod n. So, the inverse and the way you read this w to the minus 1 is not like you would do in math. This is considered the multiplicative inverse. It's not quite that, but it's close enough. So, you go with 11, so w is 11, okay? W to the n minus 2, n is 13, so n minus 2 becomes 11, so it's 11 to the 11th mod 13, okay? 11 to the 11 mod 13, okay? 11 to 11th is that big number, mod 13, and you get 6. So the multiplicative inverse of this is 6. Now, prior to about a year ago, I made you do all this math by hand. I'm actually going to show you how to do it by hand. The problem is, teaching this class online, how could I possibly guarantee you're doing it by hand? Because you know you wouldn't. I mean, out of an entire class, maybe one would. I'm sorry, it's life. We all have calculators, we all have computers, and you know this whole thing about the responseless lockdown browser, so you bring up your tablet or your other laptop or your cell phone nowadays. So I will show you how to do it by hand, but I'm no longer testing you on that because I can't require you to do it. So, all right. And remember, that was method 1. There's 10 homework assignments for calculating the inverse of W. You got to do each of them with all 3 methods. So it's basically 30 of them. That's method 1. Everybody okay on method 1?
So we do each one.
Right, I will tell you the N and the W for 10 assignments, which I will actually show you the assignment. And you'll see exactly how you got to do it. Okay? All right, here's method 2. Here is how you will see the question written, by the way, on the test. I will be telling you to calculate the multiplicative inverse of W. This is called the comparison method, which is actually the closest method to doing it correctly. And you need to know this for when we cover DES later on. I'll explain how this works. Okay. We use N and W again, the 2 numbers I'm going to give you. Okay? And what you do is you write down N, W, and C for N, W, and the number of comparisons. Then below that, you put 1, 0, 0. So you got N, W, and C. 1, 0, 0. Everybody okay so far?
So always you write 1, 0, 0.
Yes. You always write 1, 0, 0. Then you add them up. N was 13, so 13 plus 1 is 14. Plus 13 is 27. Plus 13 is 40. Plus 13, you keep going. You keep adding 13. Okay? W, you 11 plus 0 is 11. Plus 11 is 22. Plus 11 is 33. Plus 11 is 44. You keep going until they match. You go until you find a match on the W column. Then you figure out which comparison that was. Okay? So basically I checked the 0. The 0 didn't match anything. I checked the 11. The 11 didn't match anything on the N column. I checked the 22 on the N column. It doesn't match. So I keep going down until I get to 66 on the W column. And that happened to match up with 66 on the N column.
So the first line is a 0 comparison.
Right. So this is the 6th one down. So you're basically giving me the number where W matches. Don't give me where the 66 on the N column matches, because that would be a 5. Okay? Is everybody okay on how we got 6 there? It's really easy to do. But some of the numbers I give you, you'll have large results of 21 and 27 and stuff like that. But so many times, people screw up basic math. I mean, I do it. I mean, you're adding 13 plus 1 plus 13 plus 13 and you miss one, or you're off by a number and it screws up your whole thing. So if you're doing this by hand and you get into the 20s and you haven't had a match yet, you might want to check and make sure your numbers are correct. But some of the numbers you will be working on are greater than 27 or greater than 26. I think 27 is one of them. So just check your numbers. Okay? So far so good on method 2? So you can do that for 10 times. Okay? You are welcome to write an Excel spreadsheet to do it. That's how I actually came up with them. Just make sure it works correctly. Okay? So many times it doesn't. And then you're, well, that's what my Excel spreadsheet says. I don't care. That's wrong. Just give me the right number. Okay. Let's look at comparison 3. You liking my slides with like color and arrows? It was funny because Kyle Cook and them went to Tulsa. And they messaged me back, said, hey, can you send me your slides? Because Dr. Schnoy's aren't cool like this. And he doesn't explain it like this. You know, like they couldn't remember, so I had to send them my slides because they were all color-coded and everything. Okay. So now we're going to do it with the third method. Okay? This is W to the W mod N. Again, take N, take W, same numbers again. So W to the W, which is 11 to the 11th mod N, comes out to the same number. Comes out to 6. Now, it just so happens that W to the N minus 2, when using N of 11 and W of 13, you end up with 11 to the 11th. It's not always that case. Just so happens to be with this example. Okay? So don't always think they're the same number. They're not always the same. And you notice how all of the inverses came out to be 6? They're not always the same on your homework. So don't do 1. Just tell them, oh, they're all 6. You're going to get some wrong. They're not always the same. I know it's weird. But the reason is we're not using the correct numbers here. We're supposed to be using a very large 200-digit number to do this. We're using piddly numbers, and it doesn't quite work the same. But you're still getting the gist of how it would work. Okay? If you'd like me to give you numbers that are 200 digits long, that's fine. But they're very long. It's too much work. Okay? So everybody okay in the 3 methods? W to the N minus 1, or N minus 2. Comparison, then W to the W. Those are the 3 methods. I even tell you which way to do them. Okay? So far, so good? So far, we've taken our simple super increasing knapsack. We've calculated the hard knapsack. Then we've used that along with our binary numbers to encrypt the text. Then we calculated the inverse of W, the multiplicative inverse of W. All right. Now we need to decrypt something. And we need the multiplicative inverse in order to decrypt something. Okay? It's only needed for the decryption. There's a test question on calculating the hard knapsack. There's a test question on encrypting the text. There's a test question on calculating the inverse of W. And there's a test question on decrypting. Okay. All right, so let's go through this. That's from the previous slide on how to calculate the hard knapsack. Remember, it was h to the I equals W times S to the I mod N. Okay. Basically, we're just showing their equivalencies there. Okay. It doesn't matter if you know that, but really what we need to know is down here. The bullet below the remember. Okay. Don't worry about the math up here. I'm just showing you that it's the same numbers, just different positions. Okay. So remember we calculated the inverse of W. Everybody got that? Remember we had our ciphertext, the 12, 9, and 10. Okay. So we use the multiplicative inverse of W, which is 6, times the first ciphertext value, mod N, gives us our plain text. Okay. So 6 times 12, because 12 is our first ciphertext value. Okay, so 6 times 12 is equal to 72. Mod 13, which is N, okay, gives us 7. So far, so good? Up to the 7. So 72 mod 13, again, we take the 13 in front of the 72, calculate the remainder, and come up with 7. Okay? And how the heck is that 101? I'll show you. Get there in a minute. All right. So for the second number, 6 times 9. Again, 6 is the multiplicative inverse of W. 9 is the second ciphertext number. So 6 times 9 is 54. Mod 13. We end up with 2. Okay? 6 times 10 is 60. Mod 13. Again, 13 in front of the 60. We end up with 8. And 8 is not 0, 1, 1 in binary. Just don't think you're just converting it to binary. I'm going to show you what you do with that. Okay? All right. This 7, 2, and 8 right there, that's your intermediate value. It's wrong. Don't submit that as your final answer. The final answer is the 101, 010, and 011. Okay? Let me show you how to get that. But on the test, I'm going to put the 7, 2, and 8 there as well to see if you remember that that's the wrong answer. All right, so what do we do with that? Okay? All right. So we took all of our numbers, and I think this is a different example. Yeah, this is a different example now, 1, 3, and 6. Okay? So we took our hard knapsack. Okay? Our hard knapsack is 11, 7, 11, 7, 11, 7, and 1. Okay, this is our hard knapsack. I'm going to show you how to do the ending part in a second. Okay. Here's how we're encrypting our numbers. We take our hard knapsack along with our plain text. And you remember that was the whole 11 times 1 plus 7 times 0. We get our ciphertext. Okay. Then we have to decrypt them. Okay. We bring down our inverse of W in this case. Okay. Inverse of W times the first ciphertext value mod 13. Okay. And we get this 10 and this 4. Okay. Then we need to use the simple knapsack. In other words, that 10, what combination of 1, 3, and 6 is equal to 10? All of them, so it's 1, 1, 1. See that? What combination of 1, 3, and 6 is a 4? 1, 1, 0. What if I said a 7? 1, 0, 1. What if I said a 6? 0, 1. What if it was a 3? 0, 1, 0. I mean, you see how that works? The 10 and the 4 are their intermediary values. It's so close to the final. Okay, but remember, this camera did not send me the simple super increasing knapsack. But when I encrypted the text and sent it back to him, he's the only one that has that 1, 3, and 6. So he's the only one that can decrypt this number. Okay? So, it's in other words, what combination of those numbers equals that intermediate value? then that's how you come up with your plain text. Everybody good? Pretty simple? Yes, no? Hopefully. Some of you are like, okay. You're going to have to walk through this about 1,000 times. I realize that. Luckily for you, you got assignments in all this, so we're good. All right. So, let's talk about how this thing works. It's really, the modulus n, again, I think we were using 13 there a minute ago, is normally 200 bits long. So it's a very large number. So remember, the numbers we're using are just so we can do it easily. It's really 200 bits. The simple knapsack themselves, remember the 1, 3, and 6 we started with? Those are normally 2 to the 200th apart. So you can imagine how big those numbers are. What is 2 to the 200th? A lot. Okay? So those simple knapsack numbers are not 1, 3, and 6. It's a digit that is 2 to the 200th apart from each other. Okay? The knapsack itself is normally 200 terms or so. We're doing with 3 terms. They do with 200 terms. Each term is 2 to the 200th apart. So you can see very big numbers we're working with here. Okay? It says choose n random numbers between 0 and 2 to 200. No, it's just a lot. The simple knapsack is numbers that are crazy huge is what they are. Okay? Each term is 2 to the 400 digits long, or bits long. It'll take 10 to the 47th years to try 2 to the 200 choices for each digit in the simple knapsack. So remember we talked the veneer cipher was good for 300 years? I think we're a little bit beyond that with this one. It's going to take you a long time to try them all. And it's hard to break when you have very large numbers, obviously. We're working with teeny tiny 1-digit numbers. And some of you are going to have an issue with it. Imagine if I gave you a number that was 200 digits long. But again, computers make this a moot point because they can do the math. But still, the fact is they're very long, very large numbers. You know, you guys very easily looked at this and could just tell me what the answer is. But if you had something that was 200 digits long, you couldn't just look at it and tell me the answer. You'd be like, I don't know.
Rayman.
Yeah, Rayman, exactly. Okay. All right. There are some weaknesses. Shamir determined that if the modulus n is known, it's possible to determine the simple knapsack in polynomial time. So in other words, it might still take a long time because the numbers are large, but it can be determined if n is known. Okay, great. I don't know the math behind that, but he is determined. That's why I'm not a mathematician. Okay, here's exactly how you'll see it. I will give you the simple super increasing knapsack. I will give you the n and the w. I will tell you to compute the hard knapsack. Okay? Then I will tell you to compute or encrypt the number. I will give you the binary number, just like that. I'll tell you to compute the multiplicative inverse of w. Then I'm going to tell you to decrypt a different number. Okay? And it's actually very hard to come up with numbers that work perfectly on this. I think the assignments and the test, the numbers all work out, but if for some reason it just won't work for you, let me know because I might have screwed up one of the numbers. Okay? Because they're very hard to come up with numbers that work perfectly on this. Okay? So that's what the test question is going to look like. All right. Before I stop the recording, I'm going to show you what your assignment's going to look like. Okay. If you were to go into the Dropbox, you would see that. Oh, no, this is the practice. I'm sorry. This is the practice. Okay? So I give you a number. I tell you to do it with a comparison method. I tell you to do it with w to the w mod n. I tell you to do it to the w to n, w raised to the n minus 2 mod n. Okay? So there's an example. Okay? Don't be fooled. See how that comparison is very quick? A lot of times people skip over that one. They just skip it. I don't know why. They just don't even realize they match, but they do. I don't know why. It's just a lot of times one is the answer, so just watch it. Okay, so there's the practice. Let me bring up your assignment now. Okay. Your homework says go to the quizzes in D2L and do it. Okay. the assignment, I actually put this up here. Here's what it looks like. These are the right questions even. Again, the quiz isn't timed. So if you really want to open up the quiz and print it and work on it, just keep saving your answers. Just don't submit until you're finished. Don't do one of them, hit submit and say, oh, sorry. No. Okay. Here's exactly how you'll see it. Okay. Complete the calculations using the comparison method. So I tell you exactly which way to do it. All I want in there is the answer. Do not tell me n to the n minus 2 mod n is this. No, just tell me the answer is 5. Or whatever it is. Okay. So you tell me just the answer will automatically grade, and you'll be happy you get a good grade. If you put in anything else, you're going to get it all wrong. They'll be like, oh my God, I freaked out. I screwed up and put in the wrong answers. Okay, but there's the questions. You can... What? There's a text box you type it in. You just can't see it on the screen. It didn't print. Right before the ABC check, there's a text box where you just type in the answer. All they want is the 5 or the 1 or the 2 or whatever the answer is. Just put it in. But they're not always the same. Most of them are, I should say, but not all of them are. So make sure you do all of them. Okay? Any questions on the assignment? It's really pretty basic. All right? Now this one here is the answers. I'm not going to open it for you. I would, but there's this recording thing going.
Stop recording.
All right. Is everybody okay on doing this? That's all I'm going to cover tonight. Make sure you know how to do that. Walk through the... You're going to have an assignment of solving the knapsack as well. But that's the next week. I think I cover it kind of quickly again next time and then do another recording. But, okay, I mean, everybody happy? Okay, let me stop this recording.